That's too far, sorry.
Yeah, I see it today.
This one. A couple of days ago, I don't think it was yesterday, the day before, when we talked about the heat of formation, would you go back there in your notes for a second? We did an example with ammonium chloride. I had 8 grams of ammonium chloride.
Nice.
And the question was, what is delta H? Now the standard delta H is 15 kilojoules per mole. That means that when 1 mole of ammonium chloride dissolves, it should take in 15 kilojoules. I have measured out a sample of 5.35 grams of ammonium chloride. So that would be 1/10 of a mole of this stuff. Now looking at your example problem that you did, rather than plugging in 8 at the beginning, plug in 5.35. Turns out that that's 1/10 of a mole. You see the molar mass of ammonium chloride? 53.5. So this amount is 1/10 of a mole. So if the standard delta H for that process is 15 kilojoules per mole, if we cut that amount to 1/10 of a mole, how much energy should this take as it dissolves? It should be 1.5. Right. So that should cause it to be 1.5 kilojoules positive as a tenth of a mole dissolves. All right. Yes, Ellen.
Does that energy refer to like when it dissolves in water, and will it differ when the dissolving agent is different?
We're going to be dissolving in water for everything. Every dissolving thing that happens is going to be in water. Now, is that true in real life? Well, no, you can dissolve stuff in other solvents. But in here, in any time you see dissolving or whatever, it's going to imply water.
So would the energy change if it's like other dissolving?
Yes, yes it would. Yep, because the interaction. This, part of this delta H is due to the interaction of these ions with water. So if it's something other than water, the interactions are going to be different. They would. Yep. All right, can I have you do me a favor? Would you hold this, and I'm going to do the demonstration over there. I'm going to measure out 100 milliliters of water. We're going to call that 100 grams of water. And I'm going to get it as close to 100 grams as I can. Okay, that's a little bit under. Pooja, would you look at that and tell me, are we close enough to 100 grams, 100 ml to call it that? Okay. Do you see it's a little bit under?
Yeah.
The meniscus is just under the 100 mark. I'm using it anyway. Close, Girish. Give me that. Now, can I have you measure the temperature as I come over here? And the mass of the water, I've got M with a little subscript W there, is 100.0 grams. It's close to that. Girish would have gotten it right on the 100. No, he wouldn't. The C of the one we can play. Maybe in his mind he would get exactly 100.
I'll get it to the 0 and 1,000.
0, 0, 0, right. The specific heat of water is 4.18. Initial temperature?
20.8.
20.8. Thank you for going to the 10th place on that. Awesome, because if you didn't, I would have asked you, okay, give me one more sig fig. Because it's going to be a small enough change that we would like 2 sig figs for our difference, and that's perfect. Okay, thank you for that. Now, I'm going to grab, I've got just over there, a sample of 5.35 grams of ammonium chloride. All right, so with my very inexpensive piece of equipment, that really is a coffee cup, but we're calling a calorimeter to make it sound fancy. And, of course, it's precision cut lid to hold the heat in. I'm going to dump my 1/10 of a mole in, and then take the thermometer and gently stir I know you've had Chem 1 teachers that say, never stir with a thermometer. Well, if you're gentle and you don't have anything that's going to break the thermometer, then go ahead and stir. Now some will ask, hey, aren't you changing the amount of heat because there's friction due to the stirring? Well, yeah, but that's negligible. I don't think that stirring really heats it up that much. Girish, what do I do then? If I don't stir it, then the temperature will not be uniform throughout. We see how powerful that is. I don't have that kind of power. All right. Now, hopefully we have let this go long enough. Pooja, would you kindly go ahead and keep stirring and watch it over just a little bit of time. What we're trying to do, I'm going to come up with a Q for the water. How much energy did the water, what should be happening to the water's temperature again? Is it decreasing?
Yeah.
It is, okay, good. Because Q of the water should equal negative delta H of the reaction. Now the reason I have that negative sign in there is because the Q that's gained by one thing is equal to the Q that's lost by another. So the thing that lost energy is going to have a negative sign in front of it. Mathematically that works out. All right, can we have a final temperature? You do want to make sure, and you're going to be doing this on Monday, make sure that you get the final temperature and be patient with it. Because if the temperature is still changing as you're reading and you don't realize it, your data's not going to be that good. Girish? It's going to be just like this. It's going to be styrofoam cups out at every station and the fancy lids.
So does that only take like 10 minutes? So is it still going to be?
No, we're going to have two different reactions to find the delta H of. And then we're going to have to plug those into Hess's law. It'll take you a while. The experimental part is not that long. But then the write-up and the analysis is. Yeah, it's a write-up. Yeah. Pooja, sorry about.
Like 17.7.
17.3? Would you take a moment and calculate the delta H for the reaction from that data? And I'll take that from you. Thank you very much. All right, Ellen, I'll take that and put it back so you can do the problem. Thank you for that.
What is F?
Okay. So what do you get for the Q for water? How much?
1,460.
Oh, 1,460. We can only have two sig figs,
Okay.
so it's 1,500, right?
Wait, when did we use 3?
Because 5.
No.
3.5.
This minus this gets us one place past the decimal. That the delta T is what? 2.5. Negative 2.5.
Got us there.
That's right. Or is it 3.5?
It's 3.5.
3.5. Negative 3.5. Yeah.
Oh, it's final minus initial.
Final minus initial. So we get a delta H for the reaction. Now Q for the water is negative 1,500 because it lost heat. Gave it to the reaction, which is positive 1,500. Oh my goodness. Do you see what just happened? With our dollar store equipment, we predicted, theoretically, we should have a delta H of 1.5 kilojoules. And with our Betty Crocker baking oven, we got 1.5 kilojoules.
Betty Crocker baking oven.
So the equipment works, and I think it's important for you to see that. I know we joke about it, and it's funny, but I'll tell you, is this setup with two nested styrofoam cups, is that better than an actual ceramic coffee cup?
Yes,
I think it is. Why?
it doesn't lose heat.
Yeah, when you grab a ceramic coffee cup when it's got fresh coffee in it, you burn your hand because there's so much heat escaping out the side of it. What's that? Styrofoam works great. You grab a cup of hot coffee in a styrofoam cup, you can barely feel the heat. And now I've got two nested, one inside the other. Yeah, see what I mean? Two nested inside of one another. We're doubling the insulation capacity. Styrofoam is awesome. So yeah, this works great, and you can feel confident in the results that you get. And the results you get in your lab on Monday, we're going to have a very narrow window of accuracy that we're counting on, and you'll hit it if you're careful. Just make sure that the temperature change is finished when you read the temperature.
This sounds like an ad.
True. That's true. All right. Oh, this is not where we're going.
Spell.
Okay. We're not going to do this problem, but I just want you to look at it and contemplate for a moment. This is out of the book. Number 61, I believe this is one of the assigned problems for this chapter. Don't take the time and write this down because I'm going to go off of it before you have a chance to finish. Then you'll be frustrated. What was that about malaria?
Nothing.
Ha ha ha.
So we have 50 ml of a solution of silver nitrate mixed with 50 ml of a solution of HCl. And this is the reaction that happens. This is from the silver nitrate, that's from the HCl. We get a precipitate that forms. We have a thermometer in this system. We note that the initial temperature of both solutions was 22.6, and then after they're mixed together and they have a chance to react, the temperature goes up to 23.4. What does that temperature change tell you about this reaction? It's exothermic. The reaction was giving off heat to the surroundings, and the surroundings in the reaction were the water, was the water. So the water gained heat from the reaction occurring, and it went up. Now the question is, what is the heat that accompanies this reaction in kilojoules per mole? Would you be able to find how many kilojoules are given off by this reaction? Would you be able to figure out how many kilojoules per mole the reaction is? Did I use a mole of each of these? No, but I do know how many moles I used of them. You would have to use the limiting reactant. In this case, there is no limiting reactant. We have 50 ml of 0.1 molar of that, and 50 ml of 0.1 molar of that. So there's the same number of moles. Take either one of the numbers of moles and divide it into the delta H that you get. That's how we would do that problem. Anybody have any questions about that? I mean, the solutions guide there for you. I'm going to move on because I've only got just over 15 minutes left. That's what I need for the next part. Okay. The last thing, and this is the part that's out of chapter 10. The last thing involves when you have a phase change. When you have ice that's melting or water that's boiling. If you put a thermometer into water and you get it boiling, during the boiling, what are you going to notice about the temperature? The temperature goes up, 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 and then when it gets to boiling, you got all this bubbling, and it flatlines. It just stops moving. Why?
Once you reach that boiling point, can't get any.
Yep. During that phase change, all the heat that you're putting into it is not going to change the temperature, it's just going to change the physical state.
The rate.
You could change the rate of the boiling. Add more heat and it'll boil faster, but you're not going to get boiling water above 100 degrees, as long as it's pure water. So, we need to be able to calculate how much energy it takes to undergo a phase change. This is good for temperature changes. It would not be good for phase changes because the phase change doesn't have any temperature change. The temperature is constant. So we have to go to this. In a phase change, the temperature doesn't change, so we have to use, for melting, this. Q still tells us how much heat we have, but since there's no delta T, we have to use this formula.
Wait,
And this is a review. You should remember this from Chem 1.